52 million years ago, the ocean surrounding Antarctica was nothing like the frozen world we know today. The water was around 15 degrees Celsius, roughly 59 degrees Fahrenheit, warm enough to resemble the coast of California more than the waters surrounding the South Pole. And beneath that surface, something was hunting. At least 21 species of sharks were moving through these southern waters at the same time, filling the ecosystem with predators that would look completely out of place in Antarctica today. One of them was not a shark at all. A penguin nearly 1.8 meters tall, roughly 6 feet, and weighing around 91 kilograms, close to 200 pounds, was hunting in the shallows, not waddling across ice, not huddling against the cold, swimming through a warm southern sea like a predator built for speed. Farther out, something even stranger had entered the water. An early whale with a body stretching roughly 18 meters, nearly 60 feet, carried serrated, multicusped teeth that looked nothing like the teeth of whales alive today. This was not an ocean waiting to become Antarctica. It was already a complete predator ecosystem. Sharks, giant penguins, primitive whales, and countless other animals moving through water that would eventually become one of the coldest environments on Earth. Then the entire system disappeared. Not one species, not one predator. The ocean itself, the animals that lived in it, vanished from existence, and the world they occupied was eventually sealed beneath ice. Almost everything we know about that vanished ecosystem comes from one unlikely place, a remote, windswept island where fragments of its former life were preserved in stone. The deeper scientists look, the stranger the story becomes, because the predators were only part of what disappeared. Something changed the environment itself, slowly enough to leave evidence behind, but profoundly enough to erase an entire marine world, and the creatures that survived the collapse had to change with it. Tonight, we're returning to the ancient waters of Antarctica to uncover what hunted there, what happened to the ecosystem that supported them, and what the fossils left behind reveal about the world that disappeared beneath the ice. Before the first permanent ice gathered on its mountains, Antarctica belonged to a different arrangement of continents, oceans, and air. Its western edge still rested against South America, while its northern connections with Australia had only recently broken apart. The land at the bottom of the world was not yet an isolated island locked beneath a polar climate. It remained part of a broader southern geography through which water, air, and life could move with far fewer barriers. This was the Eocene epoch, a span from 56 million years ago to 34 million years ago, when Earth operated under a greenhouse climate. Carbon dioxide filled the atmosphere at concentrations far above those of the present day, reaching approximately 1,400 parts per million during the early Eocene. That abundance of greenhouse gas helped maintain a planet in which the difference between tropical and polar temperatures was much smaller than it is now. The familiar pattern of a warm equator fading into a deeply frozen pole had not yet taken shape. Antarctica itself carried the marks of that climate. Along its coastal regions, forests grew beneath skies that would now seem impossibly mild for such a latitude. Fossil pollen, leaves, and other plant remains preserve evidence of temperate woodland spreading across parts of the continent. Trees occupied ground that today lies beneath ice, snow, and exposed rock. Seasonal darkness still governed the polar year, but the absence of permanent ice allowed vegetation to establish itself through the warmer months and return across generations. The oceans surrounding those forests responded to the same planetary warmth. Near the Antarctic coastline, sea surface temperatures reached approximately 15 degrees Celsius, about 59 degrees Fahrenheit, around 52 million years ago. Even during cooler phases of the Eocene, Coastal waters remained above 5 degrees Celsius, about 41 degrees Fahrenheit. These were not merely brief moments when life tolerated unusual conditions. The warmth persisted long enough for marine communities to become deeply established, with food webs extending from microscopic organisms through fish, invertebrates, and the large predators that occupied the upper levels. The Eocene world also had a different geography beneath the surface. Antarctica had not yet developed the complete oceanic isolation that would later define its climate. Open connections to neighboring land masses influenced circulation around the continent, allowing warmer waters from lower latitudes to reach farther south. The position of the continents mattered as much as the atmosphere itself. The planet was not simply warmer everywhere, its arrangement of land and sea allowed that warmth to circulate into regions that would eventually become among the coldest on Earth. One place preserves this vanished configuration with remarkable detail. Seymour Island lies near the northeastern end of the Antarctic Peninsula, where layers of exposed sediment record millions of years of changing marine conditions. Within those layers is the La Meseta Formation, a sequence of fossil-rich sediments spanning much of the Eocene. Its rocks preserve shells, bones, teeth, pollen, and fragments of countless organisms, creating an unusually detailed record of life around ancient Antarctica. Scientists sometimes describe this formation as a Rosetta Stone for understanding Southern Hemisphere evolution because its layers preserve not just individual species, but changes through time. The lower sediments belong to a warmer world. Higher layers record the gradual transformation that followed. Each layer therefore carries a different version of Antarctica, written into sediment long before the continent became buried beneath its modern ice. What now appears to be the natural Antarctic environment was still millions of years away. The forests, the open seas, and the warm climate belonged to a planet whose geography had not yet produced the conditions necessary for permanent polar ice. Antarctica was already at the bottom of the world, but it had not yet become the Antarctica we recognize. A tooth can preserve the shape of an entire ecosystem. Across the exposed sediments of Seymour Island, thousands of years of wind have passed over fossils that once belonged to hunters moving through a sea at the opposite end of the earth. Among the most revealing are shark teeth, small objects compared with the animals that carried them, yet durable enough to survive long after cartilage, muscle, and skin disappeared. From these fragments, paleontologists have identified at least 21 shark species in the early Eocene deposits of the La Meseta Formation. That number changes the character of the ancient sea. Modern temperate coastal waters commonly support only a handful of shark species in the same nearshore region. Here, during the Eocene, the predator community was far more varied. 21 species could occupy different habitats and feeding roles without becoming simple copies of one another. Some were suited to open water, where swimming predators followed fish through the water column. Others lived closer to the bottom, moving through the seafloor environment and waiting for prey to pass within reach. The distinction matters because diversity is not merely a list of names, it is evidence of structure. When several kinds of closely related predators share one marine environment, they usually divide its resources, separating themselves by depth, body form, prey, or hunting strategy. The Antarctic sharks reveal an ocean with enough food and enough ecological space to support that division. Above the sediment, fish could gather in moving schools. Near the bottom, invertebrates and smaller animals provided another supply of energy. Between these layers, predators could specialize without all competing for the same meal. Among the sharks were squalomorphs, an ancient branch of the shark lineage that includes living dogfish, sleeper sharks, and bramble sharks. Their presence shows that the Antarctic community was already connected to lineages with a long evolutionary history and a remarkable range of body plans. These were not awkward experiments from the beginning of shark evolution, but established marine predators. By the Eocene, sharks had already persisted through more than 400 million years of changing seas, surviving three major mass extinction events and repeatedly adapting to new conditions. Their companions on the seafloor included rays. Fossil teeth preserve the evidence in places where softer tissues vanished, while fragments of mineralized cartilage provide another trace of their presence. Rays would have occupied the bottom in ways familiar from warmer continental shelves today, searching through sediments and feeding upon animals hidden beneath the surface. Their existence adds another layer to the predator network, placing hunters directly within the benthic community rather than leaving the seafloor as a simple refuge for prey. Even the teeth themselves preserve clues about the animals that carried them. Their shapes reflect differences in feeding, with some built for gripping slippery prey and others adapted to crushing or processing harder materials. A fossil bed containing many forms therefore becomes something like a scattered record of feeding strategies, each tooth marking a particular solution to life in the same sea. The remarkable part is not simply that 21 shark species existed together, it is what their coexistence requires. Such a community could only persist where prey populations were abundant and dependable enough to support many predators at once, from fish and invertebrates near the bottom to larger animals moving through open water. The sharks were therefore far more than a collection of hunters in that ancient sea. They were evidence of an entire food web functioning beneath them, rich enough to sustain one of the most diverse predator communities ever preserved from the ancient Antarctic Ocean. Long before the familiar shape of a whale became associated with gentle giants and baleen, the ocean carried a very different kind of whale. Basilosaurus moved through the Middle Eocene seas with a body so elongated that its proportions seem almost borrowed from a serpent. Yet every part of its anatomy tells a different story, one written in the bones of an early lineage that had already committed itself completely to life in the water. The name itself preserves an old mistake. When enormous fossil bones were first studied in the 19th century, their size and unfamiliar form led naturalists to interpret them as belonging to a giant marine reptile. They called the animal Basilosaurus, meaning king lizard. Later discoveries revealed the truth. The creature was an archaeocete, an early whale, and the misleading name remained attached to one of the strangest mammals ever to enter the sea. Its body could reach about 18 meters, nearly 59 feet, in length, with a narrow trunk extending far behind the rib cage. Tiny hind limbs remained at the rear, inherited from terrestrial ancestors but reduced to a vestigial condition. They were no longer capable of supporting the body on land. Propulsion came instead from the long tail and its fluke, transforming a mammalian skeleton into a body plan suited to continuous movement through open water. The head carried another clue to its way of life. Basilosaurus possessed teeth unlike those of any living baleen whale. Toward the front of the jaws, conical teeth could seize slippery prey, while farther back, larger teeth carried multiple cusps and sharp serrations. Their arrangement was built for gripping, cutting, and processing substantial food. This was not an animal filtering microscopic organisms from the sea. It was a whale with the equipment of an active hunter. Fossils show that Basilosaurus was not confined to one corner of the ancient ocean. Its remains have been discovered on several continents, including Antarctica, placing the animal in southern waters during the Middle Eocene. The Antarctic specimens belong to a period when those seas were warm enough to support a diverse marine food web. Somewhere above the seafloor, fish moved through the water column, Smaller marine mammals occupied their own niches, and this enormous whale traveled among them. Because Basilosaurus breathed air, its world had a rhythm that every marine predator inherited from its mammalian ancestry. It could hunt beneath the surface, but eventually it had to rise, lifting its head into the atmosphere before descending again. A body approaching 18 meters, nearly 59 feet, would have made each surfacing a substantial event in the ancient sea, with the long spine and tail following through the water as the animal returned to its hunting depth. Evidence from preserved stomach contents reveals what happened after those dives. Basilosaurus consumed large fish and marine mammals, demonstrating that its teeth were not merely anatomical curiosities, but working tools within a high-energy predatory lifestyle. Its size placed it near the upper reaches of the food web, where maintaining such a long body required a dependable supply of prey. That supply eventually became harder to sustain near the Eocene-Oligocene transition around 33 million years ago. Basilosaurus disappears from the global fossil record. Its disappearance coincides with one of the great reorganizations of Earth's climate, when the warm marine conditions of the Eocene gave way to a colder world, changing the distribution of prey and reshaping the seas that had supported its enormous body. The serpent-shaped whale had mastered the ocean, but its mastery depended upon a climate that did not remain. Its long reign belonged to a particular temperature, a particular circulation, and a particular abundance of life around it. Somewhere between the hunters of the open sea and the smaller creatures beneath them, another kind of whale was taking shape. Lanocetus dentacrinatus belonged to a lineage whose descendants would eventually include every living baleen whale, yet its own mouth looked nothing like the filter-feeding apparatus familiar today. It carried teeth, and its body had already reached a size that placed it among the substantial animals of the Antarctic Sea. The animal is especially important because it represents one of the earliest known branches of the Mystacete lineage. Its fossils were first excavated on Seymour Island during the 1970s, in 1974 and 1975. Although the material was not formally described until 1989, the remains include parts of the skull and jaw, along with an endocast, a natural impression preserving the shape of the brain case. From these fragments, scientists could begin reconstructing an animal that occupied an unusual point in whale evolution. Lanocetus lived near the end of the Eocene, approximately 34 to 37.8 million years ago. By then, the warm marine world preserved in the surrounding sediments was already approaching a period of profound environmental change. Yet this whale still belonged to an ocean where large-bodied predators could find enough nourishment to support substantial growth. Its existence also places an early member of the Mystacete lineage within a high-latitude ecosystem, already capable of sustaining animals of considerable size. Its estimated length was about 8 meters, roughly 26 feet, making it comparable in scale to a modern minke whale. That size would have changed its place within the food web. Lanocetus was not an insignificant animal, moving among larger hunters. Its dimensions alone would have made it difficult prey, leaving only the largest predators as plausible threats. More importantly, its size suggests that considerable energy was moving through the ecosystem and reaching the bodies of animals near its upper levels. The teeth provide an even more revealing glimpse into its life. Modern baleen whales eventually abandoned teeth altogether and developed baleen plates, flexible structures that allow them to strain small organisms from seawater. Lanocetus had not made that transition. Its jaws carried a full set of teeth, preserving an older stage in the history of the lineage. The mouth therefore represents an evolutionary crossroads where a group destined to become some of the largest filter feeders on Earth still possessed the equipment of a toothed predator. Exactly how those teeth were used remains uncertain. One possibility is suction feeding, in which powerful muscles and rapid expansion of the mouth would draw water and prey inward. Another possibility is a more direct raptorial strategy, with the teeth gripping fish or squid before the jaws closed around them. Either way, Lanocetus occupied a biological space very different from that of its distant descendants. Its presence in Antarctica may also hold clues about why mysticetes became large so early. Productive southern waters could have provided concentrated food resources, rewarding animals capable of traveling efficiently between feeding areas and carrying greater energy reserves. Such conditions may have encouraged body enlargement within the lineage before the appearance of the specialized baleen system. The possibility remains an active subject of research because the fossil record captures only scattered moments in a much longer evolutionary process. The specimen from Seymour Island therefore captures more than an unusual whale. It preserves a moment when evolution had not yet settled on the form that would later define an entire order of ocean giants. Lanocetus still carried the older tools of a toothed hunter, while its lineage was already moving toward a future based on filtering vast quantities of food from the sea. In its jaws, two stages of whale history existed together, separated not by a clean boundary, but by an animal living through the transition. The first impression of Anthropornis would have been made not by its feathers, but by its height. On the shorelines of Eocene Antarctica, this bird could stand nearly 1.8 meters, about 5 feet 11 inches, above the ground, with a mass of roughly 90 kilograms, about 200 pounds. Its proportions belonged to a world in which penguins had not yet settled into the compact forms familiar today. The species, Anthropornis nordenskjoldi, entered scientific history through fossils collected on Seymour Island in December of 1902 by the Swedish Antarctic expedition led by Otto Nordenskjöld. Those remains transformed an animal that might sound almost mythical into something much more tangible. Bone preserved in Antarctic sediment showed that giant penguins were not an isolated curiosity. They were established members of the southern marine community. Anthropornis was built around the water. Its legs supported the body on land, but its real environment began beneath the surface, where its wings had become powerful swimming structures. Yet evolution had not completely erased the architecture of its flying ancestry. A bent, vestigial joint remained within the wing, a small anatomical reminder that the flipper had been transformed from something designed for air into something designed for water. Underwater, size could become an advantage. A larger body could carry greater energy reserves and sustain longer dives, allowing a pursuit predator to follow fish through deeper portions of the coastal sea. Anthropornis would have used rapid wing strokes to propel itself, while its streamlined body reduced resistance. The same warm waters that supported dense fish populations also provided the energetic foundation for a bird capable of reaching such proportions. Its estimated stature varied with the completeness of the fossils. Some reconstructions suggest exceptional individuals may have approached 2 meters, about 6 feet 7 inches, in height and reached roughly 108 kilograms, about 238 pounds. At that scale, the largest members of the species would have stood taller than many modern adults, yet their hunting life remained entirely tied to the sea. The comparison with living penguins reveals how much had changed. The emperor penguin, the largest penguin alive today, reaches about 1.2 meters, about 3 feet 11 inches, and weighs around 45 kilograms, about 99 pounds. Anthropornis could therefore occupy nearly twice the vertical space and carry more than twice the mass of its modern relative. Its body belonged to an earlier experiment in penguin evolution, when Antarctic waters could support several large pursuit hunters. Seymour Island preserves evidence that Anthropornis was not alone in reaching this extreme size. Another giant, Paleodiptus klekowski, has been reconstructed at up to 2 meters, about 6 feet 7 inches, and approximately 115 kilograms, about 254 pounds. Its remains add another large-bodied penguin to the same broader ecosystem, suggesting that substantial fish resources were available across more than one ecological niche. The coexistence of several giant penguins changes the image of these birds from occasional oversized survivors into a genuine predator guild. Different species could have separated themselves by prey, diving depth, habitat, or timing, allowing multiple large bodies to draw energy from the same productive sea. Their wings were no longer instruments of flight. Their bodies were becoming increasingly specialized for pursuit, and their lives were shaped by an ocean that could sustain predators far larger than any penguin living today. The fossil record cannot preserve the chase itself, but it preserves the anatomy required for one. Powerful shoulders, reinforced bones, and a body shaped for repeated immersion point toward an animal whose strength was expressed through movement beneath the waves rather than through long journeys across land. In that sense, its greatest adaptations were hidden whenever it stood on shore. Beneath the swimming predators, another contest was unfolding across the sediment. The seafloor was not simply a place where smaller organisms gathered beneath the larger hunters above. It was an active community of animals competing, feeding, burrowing, and breaking apart the hard shells of their prey. In this lower realm, the ancient Antarctic Ocean had developed its own intricate hierarchy, shaped by jaws and claws rather than speed alone. Among its inhabitants were decapod crustaceans, the group that includes crabs and lobsters. Fossil remains from the La Meseta Formation place these animals within the same marine environment as the sharks, whales, penguins, and fishes preserved in the surrounding sediments. Their bodies brought a different kind of predatory machinery to the ecosystem. Instead of pursuing prey through open water, they worked close to the bottom, where shells, sediments, and crevices created a landscape filled with opportunities. One of the most important behaviors was durophagy, the breaking and crushing of hard-shelled prey. A durophagous predator can attack animals protected by shells or other rigid coverings, including clams, snails, sea urchins, and related invertebrates. For prey living on the seafloor, a predator with powerful claws or jaws changes the meaning of having a shell. Protection becomes a problem of engineering, because every increase in thickness or strength requires energy to produce and maintain. Crabs and lobsters were not alone in applying this pressure. Durophagous teleost fishes, belonging to the group of bony fishes that dominates most modern marine environments, also possess jaws capable of crushing resistant prey. Their presence created competition within the same feeding zone. A clam buried beneath the sediment might face a crab probing from above, a lobster searching through the bottom, or a fish capable of crushing its shell with a powerful bite. That competition could shape the community without any predator needing to dominate it completely. Prey that were easier to break could become less common, while individuals with stronger shells or more effective hiding places gained an advantage. Over generations, those small differences accumulated. Shell thickness, body shape, burrowing behavior, and habitat preference could all become influenced by the presence of predators that repeatedly tested the defenses of the animals below them. The result was an evolutionary arms race unfolding at a remarkably small scale. A predator developed stronger crushing structures, prey responded with heavier protection, and predators faced new challenges in overcoming that protection. Energy moved through the ecosystem in many directions, connecting microscopic organisms to shellfish, shellfish to crustaceans and fish, and those predators to the larger hunters above. The seafloor was therefore not an isolated layer beneath the rest of the ocean. It was part of the same living network. This kind of ecological pressure is familiar in productive marine environments today. Tropical and temperate continental shelves can contain dense communities where predators constantly influence which prey survive, where they live, and how their bodies are built. The Eocene Antarctic seafloor appears to have operated under comparable principles, despite its position far to the south. The fossil record preserves traces of this competition in more than the animals themselves. Shells can carry scars and fractures produced by attempted predation, while the abundance of particular body forms can reveal which defensive strategies were favored. Such fragments allow scientists to reconstruct interactions that no skeleton could preserve directly. For millions of years, this network of crushing jaws, protective shells, burrowing animals, and searching claws helped organize the Antarctic seabed. Its complexity depended on the continued presence of predators capable of applying pressure from several directions at once. When those predators eventually disappeared from Antarctic waters, the change would reach far beyond the animals that vanished. The balance governing the seafloor itself would begin to loosen, allowing an entirely different community to spread across the sediment. There is no crater beneath the Southern Ocean that marks the end of this world, no single layer of ash that divides one Antarctic ecosystem from another. The disappearance was written more gradually, across the changing chemistry of the atmosphere and the slow rearrangement of continents. For the animals living there, the forces involved were too vast to perceive, unfolding through thousands of generations. The timing leads to the Eocene-Oligocene transition, roughly 34 million years ago, when Earth's climate crossed a major threshold. By then, atmospheric carbon dioxide had been declining for millions of years. At the beginning of the Cenozoic, around 66 million years ago, volcanic activity, weathering, and the burial of carbon in sediments all influenced the long-term balance of greenhouse gases. As carbon dioxide diminished, the greenhouse warmth that had allowed polar forests and temperate seas to persist became increasingly difficult to maintain. Carbon dioxide does not need to disappear completely to alter a planet. Its concentration affects how much heat the atmosphere retains, and a sustained decline can gradually lower temperatures across the globe. Climate simulations and geological evidence indicate that falling carbon dioxide was capable of bringing Antarctica toward the threshold where large-scale ice could become stable. Once that threshold was approached, even a relatively modest additional cooling could have consequences far beyond the initial change. But the atmosphere was only part of the story. Antarctica was also changing position relative to the continents around it. For much of its earlier history, South America and Antarctica remained connected or separated by shallow passages that restricted the movement of deep ocean water. As tectonic plates continued to move, the connection weakened. The opening and deepening of a seaway between them altered the routes available to ocean currents. That tectonic explanation became especially important because Antarctica's climate depended not only on how warm the planet was, but on whether warm water could reach its shores. A continent surrounded by open ocean can exchange heat very differently from one bordered by narrow passages and neighboring land. The gradual separation of South America and Antarctica, therefore, changed the physical architecture through which southern waters circulated. Neither explanation needs to stand alone. Declining carbon dioxide could have lowered the global temperature enough to make Antarctic glaciation possible, while tectonic changes altered ocean circulation in a way that reduced the delivery of warmth to the continent. Each process strengthened the other. Cooling made ice more likely, while changing circulation made it harder for Antarctic waters to recover their former warmth. The geological record does not present this as a neat sequence in which one cause arrives and another waits its turn. Instead, several changes converge around the same interval. That convergence is part of what makes the transition so important. Climate, ocean circulation, and continental geography were interacting as parts of one planetary system, with each adjustment changing the conditions experienced by the others. For the predators of the Antarctic Sea, this distinction matters. An asteroid would have produced a sudden boundary, an abrupt interruption that could be traced to a single event. Here, the pressure accumulated differently. Temperatures shifted, habitats changed, currents reorganized, and the distribution of prey gradually followed. The ecosystem was not struck down at one instant. Its foundations were being altered while the predators continued to live within it. Among all those changes, the movement of the continents provides the clearest physical transformation. A gap opened where land had once constrained the Southern Ocean, and through that gap, the circulation of the planet began to reorganize. The predators could not perceive the motion of the crust beneath them, but their world was already being redrawn by it. The boundary between two continents can begin as something almost too small to notice. Beneath the southern oceans, rock was stretching, faulting, and sinking as the land masses that had once belonged together slowly changed their positions. What would eventually become the Drake Passage began not as a broad ocean, but as a developing gateway between South America and Antarctica. For much of earlier Earth history, these continents had been joined within Gondwana, the ancient southern supercontinent. Their connection allowed land animals and plants to move between regions that are now separated by ocean, while shallow marine environments extended around their margins. As tectonic forces continued their patient work, the crust between them began to thin. The separation was measured in geological time, yet the underlying movement could amount to many millimeters each year. Around 50 million years ago, the motion between the South American and Antarctic plates changed substantially. Geological evidence indicates that the rate of separation increased, producing extension across the region that would become the Scotia Sea and the Drake Gateway. The opening was therefore not a single tear through the crust, but a complicated sequence of fractures, subsidence, and newly forming ocean basins. At first, the connection was shallow. Ridges and elevated blocks of crust still interrupted the route, allowing seawater to pass through restricted pathways rather than providing a deep channel between the Pacific and Atlantic Oceans. Even this incomplete opening could influence circulation, because water does not need a deep passage to change where heat and nutrients travel. A shallow gateway can redirect currents, alter the position of ocean fronts, and reshape the exchange between neighboring seas. The geography continued to change. Between roughly 34 and 30 million years ago, extension produced a deeper marine connection through the developing passage. The opening of deep water did not occur everywhere at once, and geological reconstructions show that barriers remained within the region for millions of years. The pathway gradually became more continuous as seafloor spreading and tectonic movement reshaped the surrounding basins. Today, the Drake Passage spans roughly 1,000 kilometers, about 620 miles, between the southern tip of South America and the Antarctic Peninsula. Its modern width gives little sense of how complicated its birth was. What appears now as a broad stretch of ocean was assembled from fragments of crust that moved apart, sank, and were replaced by newly formed seafloor. The importance of this geography lies in what it allowed the ocean to do. Before the passage became sufficiently deep and connected, Antarctica remained partly sheltered by the arrangement of surrounding land and shallow barriers. Once a continuous route around the continent became possible, water could begin moving across a much larger circuit. The Southern Ocean was acquiring a pathway that no earlier configuration had provided. The change was not simply a matter of creating more space for seawater. It altered the geometry through which the atmosphere and ocean could exchange energy around the planet. Winds blowing over an uninterrupted ocean could now push water along a circumantarctic route rather than repeatedly encountering continental barriers. The opening of the Drake Passage was therefore a geographical event with consequences far beyond the rocks that moved apart. A narrow gateway had developed into part of a vast oceanic circuit, and Antarctica was becoming increasingly separated from the warmer waters to its north. The continents had shifted only a fraction of the distance that separates them today, yet the architecture of the Southern Ocean was already being rewritten, layer by layer, beneath an ocean that had begun to find a new path around Antarctica. The new passage did more than connect two seas. Once it became deep enough, it gave the winds a continuous path around Antarctica, and the ocean began to respond. Water started moving eastward around the continent in a vast circuit, gathering momentum across thousands of kilometers. This became the Antarctic Circumpolar Current, the largest ocean current on Earth by volume. Driven largely by the persistent westerly winds of the southern hemisphere, the current moves from west to east without meeting a continent that can force it aside. Elsewhere, major currents eventually encounter land. They bend around coastlines, divide into branches, or lose their coherence against continental barriers. Around Antarctica, the water has no such interruption. The ocean can continue its journey around the continent, carrying an immense volume from one side of the southern hemisphere to the other. Through the Drake Passage alone, the current transports approximately 130 million cubic meters of water every second. That is a specialized measure of flow, describing how much water passes a particular point over time. The Amazon River, by comparison, carries roughly 200,000 cubic meters each second. The difference is difficult to picture because the current is not a river confined to a narrow channel. It is an enormous moving band of seawater spread across the Southern Ocean. Its strength comes partly from this scale. Wind pushes the surface, friction transfers energy downward, and the Earth's rotation helps organize the movement into a broad eastward flow. As the current developed, the water surrounding Antarctica increasingly became part of its own circulation system. The boundary was not a solid wall, but a moving oceanic front, maintained by differences in temperature, density, and circulation. Inside that circuit, colder Antarctic waters could remain separated from much of the warmer water farther north. Outside it, comparatively warm currents continued moving through lower latitudes. The distinction was not absolute because ocean water still mixed across the boundary, but the exchange was increasingly restricted. Heat that had once traveled toward Antarctica could now be carried eastward before reaching the continent. This mattered because the earlier Antarctic climate depended upon access to that imported warmth. The surrounding sea had once received water from lower latitudes, allowing a high-latitude ocean to remain temperate. As the circumpolar circulation strengthened, the route for that warmth became increasingly indirect. Water approaching from the north encountered the moving boundary and was redirected into the larger eastward circuit. The transformation took time. The Antarctic Circumpolar Current did not suddenly switch on the moment a deep channel appeared. Geological evidence indicates that the passage evolved through stages, with tectonic barriers gradually lowering and deepening before a fully connected circulation became possible. Each change altered the routes available to seawater, while the winds continued to act upon an ocean whose geography was being rewritten beneath them. Over millions of years, this circulation became one of the defining features of the Southern Ocean. It connected the Pacific, Atlantic, and Indian Ocean sectors while simultaneously helping isolate Antarctica from their warmer waters. The same openness that allowed the current to travel uninterrupted also gave it extraordinary reach. There was no continental shoreline waiting ahead to absorb its momentum, no narrow passage where the flow had to squeeze through before emerging elsewhere. The entire southern circumference became part of one connected path, allowing energy and water to circulate on a scale unlike any earlier Antarctic current. What began with moving continents had become a planetary scale ocean process, carrying water around Antarctica again and again, gradually strengthening the separation between the continent and the warmth that had once reached its shores. Antarctica did not freeze because the ocean suddenly disappeared from around it. Instead, the character of that ocean changed as circulation began drawing a boundary between the continent and the warmer waters farther north. Scientists describe this condition as thermal isolation, a state in which a region becomes increasingly separated from outside heat by the movement of surrounding water. Before the circumpolar current became established, warm surface waters could travel southward from lower latitudes. Their journey carried heat toward Antarctic shores, allowing marine environments to remain temperate despite their position near the pole. Once the current strengthened into a continuous eastward flow, those pathways were redirected. Water approaching from the north was increasingly swept along the vast circuit instead of continuing toward Antarctica. The separation was not absolute, but the balance of heat had changed. Each season, less imported warmth reached the continental margin, allowing the cooling signal to persist and deepen rather than being continually erased by returning currents. Ocean circulation then began reinforcing the change. As Antarctic surface waters cooled, they became denser and sank into the deeper ocean. This process helped form cold, dense water that could spread northward along the seafloor, carrying the influence of the cooling continent far beyond its shores. At depth, these waters became part of a larger circulation that connected distant ocean basins, allowing Antarctic cooling to participate in changes across the planet. The same mechanism also helped establish the temperature contrast that defines the modern Southern Ocean. Cold water remained concentrated near Antarctica, while warmer waters persisted farther north, creating a broad thermal gradient between polar and subtropical regions. That gradient affects the movement of winds, the exchange of heat between ocean and atmosphere, and the distribution of moisture across the southern hemisphere. Antarctica was becoming not merely a cold place, but the cold center of a much larger climate system. There was another consequence beneath the surface. The circumpolar circulation contributes to the upwelling of deep water, bringing dissolved nutrients toward the sunlit ocean where microscopic life can use them. Those nutrients support enormous biological communities in the modern Southern Ocean, sustaining food webs that eventually reach fish, seabirds, seals, and whales. The same circulation that now helps make parts of the Southern Ocean exceptionally productive is therefore inseparable from the process that transformed its earlier ecology. For the animals that once occupied the warmer Antarctic Sea, however, this physical transition carried a different meaning. Sharks, giant whales, toothed whale ancestors, and enormous penguins depended on a marine environment whose temperature and food supply had developed under very different conditions. As the thermal boundary strengthened, their habitat narrowed from an entire temperate ocean toward waters increasingly dominated by cold. Species adapted to the earlier conditions could survive only while enough suitable habitat remained, and the shrinking thermal range altered where prey could gather and where predators could hunt. Nothing needed to strike the continent. No single force had to arrive with sudden violence. Wind continued to push across the Southern Ocean, seawater continued to follow gradients of temperature and density, and the widening passage between continents allowed those ordinary physical processes to operate on a planetary scale. The transformation emerged from countless movements of water, repeated over immense spans of geological time. In that sense, the circumpolar current was not an agent with a purpose. It was a consequence of geography, atmosphere, and ocean physics meeting at a particular moment in Earth's history. Yet its consequences reached into every layer of the Antarctic ecosystem, from the chemistry of deep water to the animals hunting above the seafloor. The warm world that had supported those predators was being separated from Antarctica by a boundary made entirely of moving water, without a single boundary that could be seen from the surface. The history of this vanished sea can be read in something as delicate as a shell. Buried within the calcium carbonate of fossil bivalves from the La Meseta Formation are oxygen isotopes whose proportions preserve information about the temperature of the water in which those animals lived. Their chemistry provides a kind of natural archive, allowing scientists to trace Antarctic warmth and cooling across millions of years without relying on a single dramatic event. Oxygen isotopes are especially useful because their distribution within shell material reflects both the temperature of formation and the composition of seawater. When many specimens are arranged in their geological order, individual measurements become part of a continuous climate story. The shells therefore do more than mark where ancient animals once lived. They preserve the changing physical conditions that surrounded them, including the progressive cooling that eventually reshaped their habitat. One of the most detailed records was assembled by paleoclimatologist Linda Ivany and her colleagues, using shells collected from Seymour Island. The sequence reaches back into the early Eocene, when coastal waters around Antarctica were extraordinarily warm. Around 52 million years ago, temperatures approached 15 degrees Celsius, about 59 degrees Fahrenheit. This interval, associated with the early Eocene climatic optimum, represents the high point of warmth preserved in the record. Then the temperature curve began to change. Around the same broad interval, an initial decline lowered coastal waters by several degrees Celsius over a relatively short geological interval. The shift was important because it showed that the Antarctic climate was not fixed in permanent greenhouse warmth. Even within an overall warm world, the ocean could respond to changes in atmospheric composition and circulation, moving toward a cooler state through a series of steps. A second major decline emerged around 41 million years ago. Over several million years, coastal temperatures fell by as much as 10 degrees Celsius, about 18 degrees Fahrenheit, bringing the water toward 7 degrees Celsius, about 45 degrees Fahrenheit. For an ecosystem built around warm water predators, such a change would alter more than comfort or seasonal conditions. Temperature influences metabolism, growth, reproduction, migration, and the distribution of prey, so a sustained decline could gradually rearrange an entire food web. By roughly 37 million years ago, the coastal waters had reached about 5 degrees Celsius, about 41 degrees Fahrenheit. That temperature still permitted a functioning marine ecosystem, but it represented a profound departure from the conditions under which the earlier community had developed. Species adapted to warmer water would have encountered shrinking opportunities as their physiological limits met an increasingly cool environment. The final stage arrived near the Eocene Oligocene transition around 34 million years ago. Temperatures declined toward conditions that could no longer sustain the warm water Antarctic predator community, while permanent ice began developing across the continent. The significance lies in the sequence itself. The ecosystem did not disappear after one instantaneous temperature crash. Its environmental foundation weakened through repeated cooling steps, each one narrowing the range of conditions available to organisms that had evolved within a warmer sea. Across the Eocene, the coastal ocean cooled by roughly 10 degrees Celsius, about 18 degrees Fahrenheit, from its early maximum toward the threshold of glaciation. That change unfolded across roughly 18 million years, a span long enough for generations beyond counting to experience each stage as their ordinary world. Yet geological time reveals the direction that individual lifetimes could never see. The shells remained behind, layer after layer, preserving the gradual movement of Antarctic waters from warmth toward cold, and turning the chemistry of vanished animals into a record of an ocean slowly changing its nature. Sharks began to disappear from the Antarctic record before the ocean itself reached its coldest state. Their retreat leaves a particularly revealing trace, because these animals depend strongly on the physical conditions surrounding their bodies. Most sharks are ectothermic, meaning their body temperature is governed largely by the temperature of the water. As that water cools, physiological processes can slow, reducing metabolic activity and affecting growth, reproduction, digestion, and sustained swimming. The change becomes especially visible around 41 million years ago, when the second major cooling step passed through the Antarctic record, bringing another sustained decline in coastal temperature. Fossils from Seymour Island preserve evidence that shark activity declined during this interval. Teeth remain within the sediments, showing that sharks had not vanished immediately. Yet another kind of evidence begins to thin. Invertebrate shells, bearing marks associated with predatory attacks, become less common, suggesting a reduction in the intensity of shell-crushing activity. Such traces offer a different perspective from simply counting teeth. A tooth records presence at a place and time, but damage on prey can reveal something about behavior. When sharks were actively feeding among shell-bearing animals, their attacks could fracture, puncture, or crush hard structures, leaving patterns that remained after the living animal disappeared. A decline in those marks suggests that the predators were becoming less active, even while some individuals still occupied the surrounding waters. For an ecosystem containing many shark species, a gradual reduction in activity would have consequences well beyond the predators themselves. Slower metabolism means greater energetic limits, while colder water can narrow the conditions suitable for feeding and reproduction. Hunting grounds may contract toward the remaining favorable areas, separating populations that once moved through broader coastal habitats. Species with different physiological tolerances would therefore respond at different rates, producing a drawn-out contraction rather than one synchronized disappearance. Through the later Eocene, the diverse shark community that had occupied Antarctic waters was progressively reduced. Species disappeared from local deposits one by one, while rays and other Neoselacian fishes experienced similar losses. Neoselacians are the modern group containing sharks and rays, and their retreat from Antarctic nearshore environments marked the fading of an ecological structure that had been established during the warmer part of the epoch. By the Eocene-Oligocene boundary, around 34 million years ago, almost all of the Neosalacian sharks and rays that had characterized the earlier Antarctic ecosystem were gone from its coastal waters. Their disappearance should not be confused with extinction across the planet. Many related animals persisted in warmer regions, where temperatures remained within the physiological ranges they required. The Antarctic populations were instead being displaced by a changing climate, moving northward as suitable habitat contracted. That distinction matters because it reveals the nature of this ecological loss. The predators were not erased from Earth in a single event. They were gradually excluded from a place that had once supported an unusually rich community. As their hunting pressure diminished, the animals living beneath them encountered a different balance of survival and competition. Shell-bearing invertebrates faced fewer attacks, fish encountered fewer large hunters, and the intricate pressure that had shaped the seafloor from above began to loosen. The first predators were therefore responding not to a catastrophe, but to a narrowing range of conditions, long before the final transformation of the Antarctic coastline had begun. Each degree of cooling altered the boundaries within which their bodies could function, and each retreat left more space beneath them. Across the Antarctic coastline, the disappearance of sharks became one of the earliest biological signs that the old ocean was no longer the same place. A change in the seafloor can begin with the absence of a bite. Once shell-crushing predators became scarce, the pressure that had shaped life among the sediments began to loosen. Crabs, lobsters, and crushing fish had imposed a constant filter on the animals living below the water column, favoring forms that could withstand attack. When that filter weakened, organisms that had struggled under heavy predation found room to spread. Among the most revealing newcomers in the fossil record were ophiuroids, commonly called brittle stars. These relatives of starfish have slender, flexible arms radiating from a central body and generally move across the seabed by coordinated arm movements rather than by the slow, creeping motion associated with many other echinoderms. Their bodies are vulnerable compared with heavily armored shellfish, and dense populations are difficult to maintain when large predators are continually breaking apart the communities around them. Crinoids appeared as another important component. Often called sea lilies, crinoids are echinoderms that can attach themselves to the seafloor with stalks and extend feathery arms into passing currents, collecting suspended particles for food. Their presence does not mean the ancient seabed became biologically empty. Instead, the balance of life had shifted toward animals that depended less on speed, armor, or powerful jaws, and more on persistent feeding from the surrounding water. The fossil record preserves this transition with an unusual clarity. As Durophagus predators declined, dense accumulations of brittle stars and crinoids became increasingly common. Durophagus means adapted for eating hard-shelled prey, and these predators had been an important source of ecological pressure on clams, snails, echinoderms, and other animals living across the bottom. Their retreat removed one of the forces that had kept vulnerable suspension feeders from dominating large areas. Without constant shell crushing, the evolutionary contest between predator and prey changed direction. Thick shells were no longer as universally valuable, while organisms capable of living exposed on the sediment gained opportunities that had previously been limited. The seafloor could support larger concentrations of slow-moving animals because fewer hunters were disturbing them, consuming them, or breaking apart their feeding structures. To modern eyes, the resulting community can seem strangely old. Modern Antarctic seabeds contain assemblages that share important ecological characteristics with Paleozoic marine communities, from an era when the oceans were structured by a very different collection of predators. This resemblance does not mean the organisms themselves are unchanged survivors from that distant age. Rather, familiar ecological relationships had been reassembled under conditions that favored forms once more common before modern predatory pressures became widespread. The contrast is especially striking because the earlier Antarctic seafloor had been anything but simple. Shell-crushing predators had created continual competition, forcing prey to respond through behavior, armor, habitat choice, and other adaptations. Their disappearance did not simply remove animals from the food web, it removed the selective pressure that had helped organize the community. The result was a kind of ecological release, where traits once disadvantaged by predation could become useful again, and organisms that had remained scattered could form extensive beds across the bottom. What remained was therefore not a return to some untouched original state, but an ecological reconfiguration. Brittle stars could gather in greater numbers. Crinoids could extend their feeding arms across the current, and other vulnerable organisms could occupy spaces that had once belonged to more heavily defended forms. The Antarctic seabed had not become peaceful in any absolute sense. It had become less dominated by active predation, allowing an older style of marine community to emerge within a world that had once supported a much more intensely contested seafloor over time. There is a particular kind of absence preserved in the rocks, the point where a lineage simply stops appearing. For Basilosaurus, that boundary falls remarkably close to the Eocene-Oligocene transition around 34 million years ago, when the climate system was moving into a fundamentally different state. The Great Archaeocete had occupied the oceans for millions of years, but its record does not continue beyond this geological turning point. The timing matters because the transition was not merely another cooling episode. It marked the establishment of large Antarctic ice sheets and a major reorganization of ocean temperatures, circulation, and marine habitats. Waters that had supported an exceptionally productive predator community were becoming colder and more strongly divided from the warmer regions farther north. For an animal built around a large body and a high energy demand, such a transformation could alter survival without requiring a single catastrophic blow. Basilosaurus reached roughly 18 meters, about 59 feet, in length, giving it a body plan that demanded a substantial and dependable supply of prey. Its long, serpentine form was adapted to continuous movement through the open ocean, while its teeth were suited to capturing substantial marine animals. Such a predator could tolerate changes in the abundance of individual prey species when the wider food web remained productive. A broad collapse across several levels of that web would have been different. Even a gradual decline in prey quality could matter when every hunt required substantial expenditure of energy, especially for an animal living entirely at sea. As Antarctic waters cooled, prey communities changed with them. Fish and other marine animals adapted to warmer conditions could retreat toward lower latitudes, while species associated with colder water expanded into newly suitable regions. The result was not simply less food in one place. It was a rearrangement of where food existed, when it appeared, and which predators could reach it efficiently. A large hunter, dependent on repeated access to energy-rich prey, would have faced increasing ecological costs. Unlike many sharks, whose fossil record shows that related forms survived in warmer parts of the world, Basilosaurus disappears from the known fossil record globally near this boundary. That distinction is important. Its extinction was not merely an Antarctic retreat. Whatever combination of cooling, prey redistribution, changing ocean circulation, and ecological competition affected the species appears to have reached far beyond the southern seas. At nearly the same geological interval, more modern whale groups were beginning to diversify. These later whales belonged to the lineage known as Neocetes, which eventually produced the dolphins, sperm whales, and baleen whales that would become familiar inhabitants of the world's oceans. Their early diversification did not necessarily cause the disappearance of Basilosaurus, but it may have added another layer of competition to an ecosystem already being reshaped by climate. The extinction of Basilosaurus therefore represents more than the loss of a single enormous predator. It closes the long chapter of the Archaeocetes, the earliest fully marine radiation of whales, whose bodies and lifestyles had carried cetaceans into the open ocean. Their descendants would not simply repeat that history. They would inhabit a planet whose temperatures, currents, prey distributions, and seasonal rhythms had been profoundly rearranged. For the Antarctic ecosystem, the consequence was especially stark. The largest predator that had once occupied its open waters was gone, while the conditions that had supported another animal of comparable size were disappearing with it. The vacancy was not immediately filled. Instead, the ocean itself was becoming a place where the old requirements of enormous warm water predators could no longer be met. The giant penguins did not vanish at the first sign of cooling. For a time, their bodies still moved through the changing Antarctic waters, carrying an older design into an increasingly unfamiliar food web. Their survival lasted longer than that of many sharks and whales, yet their dependence on fish placed them directly beneath a shifting layer of the ecosystem. When that layer thinned, the largest penguins had little room to compensate. Anthropornis and its relatives were pursuit predators, built to chase living prey rather than gather whatever drifted within reach. Their substantial bodies required regular access to fish, and successful hunting depended on more than the presence of prey. The fish needed to be abundant enough, energetic enough, and distributed through the water in ways that made repeated pursuit worthwhile. A predator of this kind could survive seasonal changes, but a prolonged restructuring of its entire food supply was a different challenge. As the Eocene progressed toward its colder ending, the composition of Antarctic fish communities began to change. Species adapted to warmer conditions withdrew as their habitat contracted, while the cold adapted communities that would later characterize Antarctic waters were still developing. This created an ecological interval with a reduced supply of familiar prey. The ocean was not simply becoming colder. It was passing through a period in which the old abundance was fading before a new abundance had fully taken its place. That gap mattered greatly to large pursuit predators. A smaller penguin could survive by taking smaller prey and adjusting its range, while a giant form carried greater energetic demands with every dive. The fossil record from the La Meseta Formation reflects this pressure through the late Eocene. Giant penguin diversity declined, their remains became less common, and their distribution appears to have contracted as the marine communities around them changed. The decline, therefore, appears to have followed the food web itself, from changing fish populations upward into the predators that depended upon them. Anthropornis seems to have persisted until close to the Eocene-Oligocene boundary, around 34 million years ago. Its disappearance belongs to the same broad transition that transformed the rest of the Antarctic ecosystem, although the precise sequence of causes remains difficult to reconstruct. The loss of productive warm water habitat, changes in fish communities, and the expanding influence of colder ocean conditions likely worked together rather than arriving as isolated events. Yet the story of the penguins did not end there. Their lineage survived the transformation, and penguins eventually diversified into the forms that inhabit the southern hemisphere today. Modern penguins are smaller because they occupy a different ecological landscape with different prey, different temperatures, and different pressures shaping their bodies. Their survival represents adaptation across a profound environmental boundary, not simple continuity with the giants that came before. The emperor penguin, the largest living penguin, reaches about 1.2 meters, about 4 feet in height, and weighs around 45 kilograms, about 100 pounds. Beside it, Anthropornis at roughly 1.8 meters, about 6 feet, and around 90 kilograms, about 200 pounds, belongs to another chapter of penguin history. Its scale was possible because the Eocene ocean could support a food web capable of carrying such a predator. When that food web changed, size itself became a liability. The giant penguins had not failed because their bodies were poorly designed. Their bodies had been exquisitely matched to an ecosystem that was disappearing beneath them. As the last great forms slipped from the fossil record, Antarctica was losing another group whose existence had once depended on the warmth and productivity of its ancient sea. For millions of years, the atmosphere had been changing in a direction too gradual for any single creature to notice. Carbon dioxide was slowly being removed from the air, and by the end of the Eocene, that long decline had brought the climate to a threshold where Antarctica could no longer remain permanently ice-free. At the beginning of the Eocene, atmospheric carbon dioxide may have stood near 1,400 parts per million. By the Eocene-Oligocene transition, around 34 million years ago, estimates place it near 750 parts per million. Several processes contributed to this decline. Chemical weathering of silicate rocks drew carbon dioxide from the atmosphere, while biological processes transferred carbon into sediments and the long-term carbon cycle. Lower volcanic activity also reduced one important pathway by which carbon dioxide returns to the atmosphere. Around 750 parts per million, climate models indicate that the balance supporting an ice-free Antarctica became increasingly unstable. The important change was not simply that the air became colder. Once seasonal snow could survive through more of the year, the surface began acquiring a new property that could reinforce the original cooling. Snow and ice reflect a large portion of incoming sunlight back towards space. Darker ground and open water absorb more of that energy. As reflective surfaces expanded, less solar heat remained at the surface, allowing additional ice to persist. This is known as the ice albedo feedback, and it can turn a modest initial cooling into a self-reinforcing transformation. The first frozen surfaces did not need to cover the entire continent to matter. Each expanding region altered the balance of sunlight, temperature, and seasonal melting. Ice became not merely a consequence of cooling, but an active participant in the climate system. Over time, the growing sheet spread across the interior and outward toward the coast, changing Antarctica from a landmass beneath a temperate climate into the cold continental environment recognized today. The scale of the eventual transformation is difficult to hold in the mind. Modern Antarctica is covered by an ice sheet spanning about 14 million square kilometers, about 5.4 million square miles. It stores roughly 60% of all fresh water on Earth, locked within ice, whose average thickness is about 2.2 kilometers, about 7,200 feet. Those figures describe the mature result of a process that began when atmospheric conditions crossed a much smaller threshold. Carbon dioxide decline alone does not fully explain why Antarctica froze when it did. The opening of the Drake Passage and the developing Antarctic Circumpolar Current had already altered the pathways through which heat moved around the southern oceans. As atmospheric carbon dioxide fell, the planetary climate became more favorable to glaciation. As circulation around Antarctica became increasingly isolated, Warm ocean water had greater difficulty reaching the continent. Each process strengthened the influence of the other. By the Eocene-Oligocene transition, these changes had converged. The atmosphere no longer supplied enough greenhouse warming to preserve the old Antarctic climate indefinitely, while the surrounding ocean was becoming increasingly separated from warmer waters farther north. Once substantial ice formed, its reflective surface reinforced the cooling and helped maintain the transformation. The ancient predators did not disappear because a single event struck their world. Their ocean was changed by thresholds, feedbacks, shifting currents, and atmospheric chemistry acting together across geological time. The ice sheet was the visible expression of that deeper transformation, preserving in frozen form the moment when Antarctica became a fundamentally different part of the Earth system. The transformation did not unfold at the same pace as the cooling that prepared the world for it. Once the Antarctic climate crossed the threshold for sustained ice, the landscape could change with remarkable speed. Climate models indicate that the transition from an ice-free continent to continent-scale glaciation may have occurred in fewer than 100,000 years, a span almost impossible to distinguish from an instant when measured against geological time. For a planet accustomed to change measured in millions of years, such a compressed interval carries a different significance. 100,000 years can contain countless generations of animals, yet it represents only a thin layer within the history of Earth. The climate had spent millions of years becoming suitable for glaciation, but the final establishment of the ice sheet did not need another long age to unfold. The conditions had been prepared long before the ice arrived. Much of the acceleration came from a property already present in the first patches of frozen ground. Ice and snow reflect incoming sunlight far more effectively than darker rock, soil, or open water. As reflective surfaces expanded across the Antarctic highlands, the continent absorbed less solar energy. Surface temperatures fell, allowing more snow to survive from one season into the next. That additional snow increased the reflective area, which reduced heating still further. The process became self-reinforcing. This feedback changed the character of the transformation. The tectonic movements that had opened the Southern Ocean had unfolded over immense stretches of time, while the decline of atmospheric carbon dioxide had also progressed gradually. Once enough cooling had accumulated, however, the physical relationship between sunlight and ice could amplify the change without requiring another equally large shift in the original causes. A small increase in persistent ice could produce more reflection, more cooling, and greater ice retention. Across the continent, those effects could build upon one another. Snow accumulating at higher elevations could remain through warmer seasons, while ice spreading outward altered the surface beneath it. The growing sheet also changed the exchange of heat between land, ocean, and atmosphere, allowing the cold interior to become increasingly distinct from the surrounding sea. Each new layer was both evidence of cooling and another surface capable of preserving it. Evidence for the abruptness of this transition is also preserved in microscopic life. Marine sediments from Antarctica contain fossil remains of dinoflagellates, single-celled organisms whose resistant structures can survive burial and become part of the geological record. Their communities reflect the waters in which they lived. Warm water species that had occupied the Antarctic marine environment through the Eocene disappear from the record near the Eocene-Oligocene boundary, while cold adapted forms become more prominent. The shift is recorded within a remarkably narrow interval of sediment, giving the transition a sharpness that contrasts with the long cooling beforehand. The disappearance of those warm water plankton communities mattered because they occupied the foundation of the marine food web. Their decline signaled more than a change in microscopic life. It marked the loss of the environmental conditions that had supported larger organisms, from fish to giant penguins and marine predators. The biological record, therefore, carries the same message as the climate models. The Antarctic system had crossed into a new state. What had taken roughly 18 million years of cooling to prepare could be completed within less than 100,000 years. The difference was not a contradiction. Slow geological processes had built the conditions, while a powerful climatic feedback compressed the final transformation. Antarctica did not simply become colder, it crossed a threshold where ice could sustain and enlarge itself, and the warm ocean that had surrounded the continent was replaced by a fundamentally different world. The Antarctic Ocean did not become empty when its great predators disappeared. Instead, the structure of life was stripped down, leaving open spaces where familiar hunters had once shaped every level of the food web. The change was not a single absence, but a rearrangement of relationships. Sharks no longer patrolled the coastal waters. Basilosaurus and other ancient whales had vanished. Giant penguins were fading from the record, and the shell-crushing predators of the seafloor had largely withdrawn. What remained belonged mostly to smaller and less conspicuous parts of the earlier community. Invertebrates persisted among the sediments. Microorganisms continued to sustain the lower levels of marine production, and cold-tolerant fish began to occupy waters that had become increasingly difficult for the warm water fauna. Yet survival alone did not restore the old ecosystem. A predator niche is more than a vacant space. It is a missing pressure that changes the behavior, abundance, body form, and distribution of everything beneath it. Without large hunters, prey populations could respond differently to seasonal resources. Without shell crushers, animals living within hard coverings faced a different selective landscape. Without pursuit predators in open water, smaller fish no longer encountered the same risks that had shaped their movements. The result was an ocean between ecological eras. The older community had been assembled around warmth, abundant fish, active predation, and intense competition among large animals. The new environment offered none of those conditions in their previous combination. Sea temperatures approached the freezing point of seawater, while the circulation of the Southern Ocean carried cold conditions across enormous distances. The animals that remained were therefore not simply survivors of a disaster. They were the beginnings of a community selected by an entirely different physical world. Vacant niches created opportunities, but opportunity alone could not fill them. Any lineage capable of becoming a major predator in the new Southern Ocean would have to tolerate extreme cold, function efficiently in dense seawater, and find enough food to support its metabolism. That combination sharply narrowed the field. Many familiar marine fish were poorly suited to such conditions, particularly those whose physiology depended on warmer water. Among the fish already present was an inconspicuous lineage called the notothenioids. During the warm Eocene, they had not been the dominant vertebrates of Antarctic waters. They occupied a relatively modest place within the broader marine community, lacking the imposing size of the predators that had commanded the ecosystem. Yet their ancestry carried traits that would become valuable as the climate continued its long descent. Cold introduced a problem that ordinary fish physiology could not easily solve. Seawater near its freezing point can cause the fluids inside an unprotected fish to form ice crystals, a process that can be fatal. Notothenioids eventually evolved specialized antifreeze proteins that bind to tiny ice crystals and prevent them from growing. This adaptation did more than preserve individual animals. It opened an ecological doorway. Once these fish could remain active in water that excluded many competitors, natural selection had room to reshape them. Some lineages moved toward the seafloor, others occupied the water column, and still others developed unusual feeding strategies suited to the emerging Southern Ocean. Their bodies, behaviors, and physiology began diverging as different populations encountered different resources and habitats. The transformation would take millions of years, but its starting point was remarkably humble. The animals that inherited the Antarctic ecosystem were not descendants of the largest rulers that had vanished. They came from a lineage that had once been easy to overlook, and the extreme environment that erased the old order would become the very force that allowed these small fish to diversify into something entirely new. Among the fish that remained was a lineage whose importance had once been easy to overlook. Notothenioids are a suborder of ray-finned fishes, ancestrally associated with the seafloor, and their relatives were already living around Antarctica during the Eocene. In the warmer marine world, however, they occupied modest ecological roles. Larger predators and more active fish controlled much of the available food, while the notothenioids remained close to the margins of the community. That position changed as the old food web unraveled. When the dominant warm water predators disappeared, the notothenioids were no longer competing for the same narrow spaces beneath a crowded hierarchy. Habitat that had once been controlled by larger fish became available, and populations that had previously been restricted could spread into new depths, feeding zones, and coastal environments. Evolution did not need to invent an entirely new lineage. It only needed to reshape one that was already present. Over millions of years, this reshaping became an adaptive radiation, a process in which one ancestral lineage diversifies into many forms, each suited to a different ecological role. Some notothenioids became hunters in open water. Others remained associated with the seafloor, where they could search among sediments and rocks. Still others evolved bodies suited to particular depths, currents, and sources of food. The result was not simply an increase in species, it was the construction of an entire vertebrate community from a relatively inconspicuous starting point. Today, notothenioids include more than 120 described species, with roughly 100 occurring only in the Southern Ocean. Together, they account for more than 90% of the fish biomass around Antarctica. Their dominance is remarkable partly because the lineage did not begin as the obvious successor to the great predators that vanished. The ecological vacancy created by cooling gave them an opportunity, but opportunity was only the beginning. Their survival depended on solving a physical problem that had become increasingly severe as the ocean approached its freezing point. For most vertebrates, body fluids contain enough dissolved substances to remain liquid at ordinary ocean temperatures. Antarctic seawater presents a different challenge. Because salts lower the freezing point of water, seawater can remain liquid at temperatures below the freezing point of fresh water, yet the fluids inside a fish are still vulnerable to the formation of ice crystals. A single crystal entering the bloodstream or tissues can become dangerous as it grows. Notothenioids evolved a remarkable solution in the form of antifreeze proteins. These molecules circulate through their body fluids and attach to microscopic ice crystals, preventing those crystals from enlarging into structures capable of damaging cells. The adaptation effectively lowered the thermal boundary at which these fish could remain alive, allowing them to exploit water that excluded most competing vertebrates. Other changes followed. Many Antarctic notothenioids developed reduced or absent swim bladders, altering how they control buoyancy while some evolved unusually lightweight bones and increased lipid stores that help them remain suspended with less effort. Their bodies became experiments in living physiology, shaped by an environment where ordinary fish design offered fewer advantages. Even their blood and tissues became part of this long adaptation, tuned to conditions that had once been beyond the reach of most marine vertebrates. What began as a minor lineage, therefore became something much larger. The cold did not merely preserve the notothenioids after the disappearance of the old predators. It opened an evolutionary landscape in which their unusual traits could become advantages, their habitats could expand, and their descendants could occupy roles that had once belonged to animals far larger and more powerful. The blood of a notothenioid carries a molecular defense, unlike almost anything found in other vertebrates. In the Southern Ocean, seawater can reach about minus 1.86 degrees Celsius, about 28.6 degrees Fahrenheit, cold enough to remain liquid because dissolved salts depress its freezing point. For most fish, exposure to such conditions would place the fluids inside their bodies dangerously close to crystallization. Notothenioids evolved a way to remain alive at that boundary, using proteins that interfere with the growth of ice before it can overwhelm their tissues. The discovery of this adaptation began in the late 1960s, when biologist Arthur DeVries studied Antarctic fish at the University of Illinois. His experiments revealed unusual substances in their blood that lowered the temperature at which ice could grow. These were antifreeze glycoproteins, molecules made from protein joined with attached sugars. Rather than changing the freezing point of the entire ocean around the fish, they work inside the animal, protecting its internal fluids from the formation and expansion of ice. The mechanism is remarkably physical. When a microscopic ice crystal enters the body, an antifreeze glycoprotein can attach itself to the crystal surface. That coating interrupts the orderly addition of water molecules required for the crystal to enlarge. A tiny fragment that might otherwise become a growing structure is therefore held in check. The protein does not need to destroy the ice. It only needs to prevent that first small crystal from becoming large enough to damage cells and tissues. This defense became one of the clearest examples of evolutionary innovation in a vertebrate. The genetic instructions for notothenioid antifreeze proteins appear to have originated from a duplicated gene related to trypsinogen, a precursor involved in digestion. Through mutation and natural selection, a copy of an existing gene was gradually transformed until its product served an entirely different purpose. A molecule associated with digestion became part of a system that allowed a fish to inhabit water close to its physical freezing limit. Protection also had to extend beyond the bloodstream. Antifreeze glycoproteins occur throughout the bodies of these fish, including the blood, liver, spleen, reproductive fluids, and the fluids surrounding developing embryos. Such distribution matters because ice does not respect the boundaries between organs. A vulnerable compartment could become a point of failure even if the circulation remained protected. By spreading the defense through internal fluids, evolution created a whole body capable of operating within the Antarctic thermal regime. Yet the adaptation carries an unusual cost. Research has shown that the same antifreeze proteins that prevent ice from growing can also inhibit the melting of ice crystals already present inside the fish. During warmer periods, those crystals may persist instead of disappearing completely. Some Antarctic notothenioids can therefore accumulate internal ice over their lifetimes, carrying remnants of the environment inside their own bodies. It is an elegant trade-off shaped by an extreme habitat. The proteins do not make the fish immune to ice in every sense. They keep ice from becoming biologically destructive, even when the surrounding seawater remains cold enough to freeze ordinary body fluids. Survival here depends not on escaping the physical rules of water, but on modifying the way those rules operate within living tissue. The blood itself becomes part of the adaptation, carrying a molecular shield that allows an entire lineage to remain active where most vertebrate life could not endure. Every drop becomes a small meeting place between biology and the freezing point, where survival depends upon controlling a process that ordinary chemistry would otherwise readily allow to continue unchecked for generations. The first thing that disappears from an ice fish is not its color, but the familiar machinery that gives most vertebrate blood its red appearance. Ice fish belong to the family Channicthiidae, a lineage of nototheniod fishes whose members have taken adaptation to Antarctic cold farther than any other vertebrate known. Their blood is translucent, sometimes appearing almost colorless or faintly yellow, because these animals lack functional hemoglobin, the oxygen-carrying protein normally packed inside red blood cells. For nearly every vertebrate, losing hemoglobin would be disastrous. Hemoglobin allows blood to collect oxygen at the gills and transport large quantities of it through the body, delivering the gas wherever metabolism requires it. Without that molecular cargo, ordinary blood plasma can carry only a small amount of dissolved oxygen. An ice fish should therefore face a fundamental physiological limit, especially while moving through water close to its freezing point. Yet the Southern Ocean offers an unusual chemical advantage. At roughly minus 1.86 degrees Celsius, about 28.6 degrees Fahrenheit, seawater can hold considerably more dissolved oxygen than warmer water. Cold water absorbs oxygen efficiently, and the waters surrounding Antarctica are also continually renewed by circulation and mixing. For an ice fish, this creates an environment where oxygen is abundant enough to compensate, at least partly, for the enormous loss in blood oxygen carrying capacity. Instead of loading oxygen onto hemoglobin, the ice fish allows oxygen to remain dissolved directly in its plasma. Every heartbeat moves this oxygen-rich fluid through an expanded circulatory system, where broad blood vessels help maintain the flow. The strategy is inefficient compared with hemoglobin-based transport, but efficiency is not the only measure that matters. In a cold ocean saturated with oxygen, an arrangement that would fail almost anywhere else can remain workable. The heart itself reveals the scale of this compromise. Ice fish species evolved unusually large hearts relative to their bodies, capable of pumping substantial volumes of blood with each contraction. Their vessels are also wider than those of many related fishes. These changes help move enough oxygen-bearing plasma toward tissues, despite the reduced concentration of oxygen that each unit of blood can carry. The circulatory system has effectively been enlarged to compensate for what the blood itself has lost. The adaptations extend beyond circulation. Most ice fish species lack functional myoglobin, the protein that stores oxygen within muscle cells. They have also experienced losses or reductions in parts of the cellular heat shock response, a system that helps many organisms protect proteins when temperatures become dangerously high. In Antarctica, extreme heat is not the recurring problem their ancestors faced, so some components of that emergency machinery became less important over evolutionary time. Their genomes also contain changes in genes associated with daily biological rhythms. Under Antarctic seasonal light, the usual alternation between day and night can become profoundly distorted, with long periods of continuous daylight followed by prolonged darkness. The internal timing systems of ice fish reflect life within that unusual cycle, where environmental cues differ sharply from those experienced by fishes living farther north. Nothing about the ice fish is merely a smaller adjustment to cold. Its body has been reorganized around a rare conjunction of physical conditions: frigid water, abundant dissolved oxygen, and an evolutionary history long enough for extraordinary compromises to become viable. Blood no longer needs to be red. Muscle can function with reduced oxygen storage. The heart can become oversized to move a fluid that carries less oxygen per volume. What appears at first to be a loss of essential machinery becomes, within this particular ocean, a different way of solving the same biological problem. Some landscapes preserve their history by hiding it, but Seymour Island does the opposite. Its exposed ground offers a rare opening into an Antarctic past that is almost entirely concealed elsewhere. The island, also known as Marambio Island in Argentina, lies off the northeastern tip of the Antarctic Peninsula, roughly 960 kilometers, about 600 miles, south of the Drake Passage. Its position places it close to one of the great geographical boundaries in this story, yet the evidence beneath its surface reaches much farther back than the ocean circulation that eventually transformed Antarctica. Seymour Island is unusually accessible because much of its surface remains free of permanent ice. Broad stretches of sedimentary rock lie exposed beneath the polar sky, shaped by wind, weather, and the slow wearing of the landscape. Across most of Antarctica, geological history is hidden beneath an enormous ice sheet, with ancient rocks and sediments sealed beneath layers reaching several kilometers, about several miles, in thickness. On Seymour Island, however, the past rises close enough to the surface to be collected, measured, and placed into sequence. The La Meseta Formation forms the heart of this record. Its layered sediments accumulated in marine environments through much of the Eocene, preserving successive communities as the surrounding climate changed. Lower layers contain evidence from the warmer portion of that epoch, while younger sediments record the progressive transformation of Antarctic waters toward the conditions that preceded permanent continental glaciation. The value of the formation lies not in a single spectacular fossil, but in the continuity of the archive. Shells, teeth, bones, and other remains occur within a geological sequence that allows scientists to compare one biological community with another across immense spans of time. For this reason, Seymour Island has become one of the most important fossil localities in the southern hemisphere. Paleontologists have described it as a kind of Rosetta Stone for Antarctic evolution because its fossils connect environmental change with the rise and disappearance of particular animals. The record includes sharks, whales, penguins, mollusks, and many less familiar organisms, allowing researchers to trace changes in predators, prey, body size, and ecological roles through successive layers. The first fossil collections from Seymour Island were made in 1902. Much later, systematic scientific expeditions expanded the work, especially from the 1970s onward, and specimens gathered from the formation have continued to produce new species and new interpretations. Each discovery adds another small piece to a record that is valuable precisely because so much of Antarctica remains inaccessible beneath ice. The exposed layers also preserve something unusual in paleontology: the order of ecological change itself. Fossils are not scattered randomly through the rocks. Their positions allow scientists to place biological appearances and disappearances against changing sediments, giving the island a temporal structure that turns individual remains into part of a larger environmental history. The result is a record where extinction, migration, and ecological replacement can be followed almost layer by layer through the exposed formation. Today, the island stands within the Weddell Sea, a region defined by cold water and extensive sea ice. That setting makes the fossils beneath its surface seem almost like an imprint from another planet. Yet they are fragments of the same ocean, preserved before the circulation around Antarctica became fully established and before the continent entered its long glacial age. A shark tooth, a penguin bone, or part of a whale jaw is therefore more than an isolated fossil. Each is a physical trace of an ecosystem that once occupied these shores, held in stone where the vanished sea can still be read. For millions of years, the Antarctic seafloor existed without one of the most familiar forces in marine evolution, animals built to break shells. Crabs and lobsters had disappeared from these waters near the end of the Eocene, leaving generations of clams, snails, and other shelled invertebrates to develop without the pressure that once favored heavier armor. That absence lasted for roughly 34 million years, long enough for an entire ecological history to unfold without a major shell-crushing predator. Now the boundary that kept such animals away is beginning to soften. Modern warming is raising temperatures around Antarctica, including parts of the continental shelf, where cold water once acted as a powerful biological barrier. The change does not require tropical conditions or anything resembling the temperatures of the ancient Eocene Sea. For a species living close to its thermal limit, even a small shift can expand the area where its metabolism functions efficiently, allowing a population to occupy places that were previously inaccessible. One of the clearest examples involves the Antarctic king crab, Paralomus burstini. Populations have been observed in the Palmer Deep, a basin lying west of the Antarctic Peninsula, where the surrounding water is only slightly warmer than the threshold these crabs require. Their presence matters because the animals are not simply surviving at the edge of their former range. Surveys have recorded increasing densities, while individuals have been found progressively closer to shallower portions of the Antarctic shelf. That movement places an ancient ecological relationship on a very different coastline. King crabs are powerful benthic predators, capable of handling prey protected by shells and hard coverings. Their return would therefore introduce a feeding strategy and a form of mechanical predation that Antarctic shelf communities have not experienced for geological ages. The significance lies not only in what the crabs could consume, but in what their presence could begin to select for among the animals living around them. A clam that has never needed a thick shell does not carry the evolutionary history of a population repeatedly tested by crushing claws. A snail without generations of exposure to such predators has no inherited memory of that particular danger. Scientists sometimes describe these animals as naive prey, meaning prey populations that have had little or no evolutionary opportunity to develop defenses against a predator they have never encountered. The consequences could spread beyond individual species and across several layers of the benthic community. Removing or reducing one kind of benthic invertebrate can alter the food available to scavengers, predators, and competitors, while changes in burrowing, grazing, and sediment disturbance can reshape the seafloor itself. A returning crab would therefore become part of a chain of ecological changes rather than an isolated addition to the community. There is also a deeper distinction between recovery and return. The ancient warm ocean is not being restored, and the animals moving southward are not simply replacing the predators that vanished during the Eocene cooling. The modern Antarctic ecosystem has spent 34 million years developing under different physical and biological conditions. Its present inhabitants belong to a world shaped by prolonged cold, glaciation, and the absence of shell-crushing hunters. If warming continues to open the shelf to king crabs, the result will be an encounter between a predator and prey community separated by an immense stretch of evolutionary time. The crab arrives carrying an old ecological role, but it enters an ecosystem that has become something entirely different in its absence. The meeting is not a return to the past. It is a new chapter written into a seafloor that evolved without the pressure of claws. A predator can disappear from a habitat for so long that its absence becomes part of the habitat itself. Across the Antarctic seafloor, that absence has lasted roughly 34 million years. During that immense interval, generations of animals have lived without the crushing claws of crabs or the hard jaws of predatory fish, selecting which shells survive. Defensive traits that once carried value could become burdens because building thicker shells, deeper armor, or elaborate escape structures requires energy that can instead be spent on growth and reproduction. The modern benthic community reflects that long history. Brittle stars spread their delicate arms across the sediment, while crinoids, or sea lilies, gather food from the surrounding water with feather-like structures. Brachiopods, sometimes called lampshells, remain especially distinctive. These ancient invertebrates have persisted since the Paleozoic era and occupy seafloor habitats where they face far less shell-crushing pressure than their relatives in many warmer oceans. Their abundance in Antarctica is therefore not simply a consequence of cold, it is also a consequence of what is missing. Across much of the world's oceans, crabs and other durophagous predators helped shape the bodies and behaviors of bottom-dwelling animals for millions of years. Their presence favored shells that could resist crushing, burrows that offered rapid refuge, and life strategies that reduced exposure on the open sediment. Antarctic invertebrates developed under a different set of rules. Without those predators, there was little reason for natural selection to preserve costly defenses against them. That difference creates an unusual vulnerability. If king crabs established themselves across the Antarctic shelf, they would not be entering an ecosystem already prepared for their arrival. They would be introducing a powerful selective force to animals that have never encountered it during their evolutionary history. A crab feeding across the seafloor could exploit prey that have no inherited behavioral pattern specifically shaped around avoiding such an attacker. Shell thickness alone would not solve the problem, because vulnerability can also depend on movement, burrowing depth, body shape, reproductive timing, and where an animal chooses to live. Evolution could eventually respond, but the timescale is uncertain. Adaptation requires variation and many generations for natural selection to increase protective traits within a population. Antarctic cold also slows many biological processes, including growth and reproduction, which can lengthen the interval between generations. A species reproducing slowly may have fewer opportunities to respond, while a newly arrived predator is already consuming individuals. The ecological consequences could reach beyond the animals directly taken by crabs. Changing the abundance of grazers, suspension feeders, burrowers, and scavengers can alter how nutrients move through sediments and how energy passes between organisms. Predation can reshape an entire benthic community, even when the predator itself occupies only one part of the food web. In this sense, the arrival of a crab would represent more than a new mouth on the seafloor. It would restore a pressure that has been absent since the Antarctic Ocean crossed into its long glacial chapter. There is an unusual symmetry in that possibility. The ancient predators disappeared as the world cooled, and their disappearance helped create the ecological character of modern Antarctica. Now warming is weakening the same thermal boundary that once kept them away. Even the most ordinary movement across the sediment has been shaped by this history, because survival has been governed by competition, temperature, food, and currents, rather than by hiding from claws. Their vulnerability is written not in fear, but in anatomy, behavior, and the long record of what never returned. Long before an animal ever enters the water, the outline of a continent has already begun shaping its possibilities. Coastlines determine where currents can travel, mountains redirect winds, and narrow passages can connect seas that would otherwise remain apart. Biology follows these physical arrangements with extraordinary precision, building communities from the opportunities that geography provides. Antarctica offers one of the clearest examples because the animals that once lived around it were governed by a landscape that no longer exists. The sharks, ancient whales, giant penguins, and other predators of the warm Antarctic Ocean were not separated from extinction by some special evolutionary advantage. Their survival depended upon conditions that allowed their bodies and hunting strategies to function. Antarctica could remain connected to warmer ocean systems, while South America still stood close enough to interrupt the circulation that would later develop around the continent. Water could reach the Antarctic margin, carrying heat and supporting a food web that extended from microscopic organisms to enormous predators. Then the geography changed. As the tectonic plates shifted, the distance between Antarctica and South America increased. The opening eventually formed the Drake Passage, a broad marine gateway roughly 965 kilometers, about 600 miles, across at its narrowest extent. Its importance did not come from its size alone. Once continuous deep water connected the Pacific and Atlantic Oceans around Antarctica, a new pathway became available for a current to circulate around the continent without encountering another landmass. That rearrangement altered the movement of heat. Water that had once reached Antarctic shores more readily was redirected into a circulation system that increasingly isolated the continent from lower latitude warmth. The biological consequences followed because temperature is not merely a background condition for life. It determines metabolism, growth, reproduction, prey availability, and the physical limits within which tissues can function. Nothing about the ancient sharks needed to become weaker for them to disappear. The giant whales did not suddenly lose their adaptations. The enormous penguins did not become less capable hunters. Their environment simply withdrew the conditions that had made those adaptations useful. A predator can be perfectly suited to its world and still vanish when the world changes around it. This principle appears throughout Earth's history. The Great American Interchange began when the continents became connected by a land bridge, allowing mammals and other animals to cross between North and South America. Australia's distinctive fauna developed under a very different history of geographic isolation. The changing connections between the Mediterranean and surrounding seas likewise transformed its climate and marine life. In each case, geography did not dictate every evolutionary outcome, but it established the boundaries within which evolution could operate. Antarctica makes that relationship especially visible because the sequence can be traced through both rocks and living organisms. A continent moved, a passage opened, ocean circulation reorganized, temperatures changed, ice expanded, predators disappeared, other lineages diversified into the spaces left behind. The chain contains no single moment when geography became biology. Instead, each physical change altered the possibilities available to life, and natural selection worked within those new possibilities. The Antarctic ecosystem that exists today therefore carries the memory of continental motion in its anatomy, its food webs, and even its most unusual biochemical adaptations. The antifreeze proteins of notothenoid fish, the extraordinary circulation of ice fish, and the absence of many ancient predator groups all belong to the same geographic history. They are biological answers to conditions created by moving rock, circulating water, and changing climate. For roughly 35 million years, the Southern Ocean has remained within the broad environmental legacy of that transformation. Beneath the ice, the living community continues to reflect a map that was drawn by tectonic movement long before any of its present inhabitants existed. Geography became climate, climate became selection, and selection became biology, leaving the shape of a vanished world written into the life that followed. The warm Antarctic ecosystem did not arrive all at once. Its foundations were already taking shape when the early Eocene began, roughly 56 million years ago, and some of its deeper ecological ancestry reached back farther into the upheaval following the Cretaceous Paleogene extinction. Across immense spans of time, predators and prey became linked by repeated encounters. Sharks refined their hunting, whales entered new feeding roles. Penguins developed bodies suited to pursuit beneath the waves. Crabs occupied the seafloor as shell-crushing predators. None of these relationships belonged to a single moment. They accumulated through countless generations, each generation altering the conditions experienced by the next. Across those depths of time, extinction was not the absence of change, but one of its forms, as familiar lineages gave way to others, while the larger architecture remained recognizable. For millions of years, the Antarctic margin provided a setting in which those relationships could persist. Species disappeared and others replaced them, yet the broader structure endured. A predator could specialize because prey remained available. Prey could develop defenses because predators remained present. Competition shaped where animals fed, how they moved, and which parts of the ocean they occupied. Over geological time, such interactions become woven into anatomy itself. The ecosystem was not simply a collection of species living together. It was a network continually adjusted by the presence of its members. Then the scale of change became strangely compressed. The transition from an ice-free Antarctic to continent-scale glaciation occurred in fewer than 100,000 years. To human perception, that interval is almost impossibly long. It exceeds the entire span of written history by many times. Yet, in geological terms, it is a narrow boundary, a brief passage between two radically different states of the planet. The rocks of Seymour Island preserve this contrast with unusual clarity. Sediments accumulated layer by layer, recording changing communities through the Eocene and into the colder world that followed. A thickness of only a few centimeters, about an inch, can represent thousands of years of environmental history. Across a much larger vertical sequence, millions of years are compressed into something that a person can examine within the length of an afternoon. The scale of the record is physical, but the time contained inside it is almost impossible to hold in the mind. Human civilization occupies only a tiny interval within that greater chronology. The first cities appeared roughly 10,000 years ago, while the Antarctic predator ecosystem had already been developing for millions of years before any human settlement existed. Even the entire history of anatomically modern humans represents only a fraction of the time involved in the transformation from warm Antarctic seas to the glacial Southern Ocean. There is another scale beyond even this immense history. Earth itself is about 4.5 billion years old. Against that span, the entire Eocene Antarctic story occupies only a small portion of planetary time. Its warm seas, flourishing predators, rapid cooling, and expanding ice are concentrated into a geological interval that is brief when measured against the life of the planet. That contrast gives the fossil record its particular character. A layer of rock can preserve an ecosystem that existed for millions of years, while the boundary separating it from the next world may represent only a fraction of that duration. The animals vanished within an instant by geological standards, but the conditions that created them had taken ages to assemble. Time built the web slowly, then geography and climate altered it within a span too short for geology to call gradual. The Antarctica, held in the modern imagination, is almost entirely a product of recent geological history. That image feels timeless only because the transformations that created it unfolded far beyond the scale of ordinary human memory. Its apparent permanence is therefore an illusion created by brevity. Its white expanses, breeding emperor penguins, Weddell seals, and icefish seem inseparable from the continent itself, as though they had always occupied these shores. Yet the fossil record preserves another Antarctica beneath that familiar image, one where the waters supported a far broader community of predators, swimmers, and bottom dwellers. The modern ecosystem is not the original pattern of Antarctic life. It is the arrangement that remained after an older world disappeared. When the great cooling transformed the continent, the species that could tolerate the new conditions became the foundation of what followed. Some were survivors of the older community. Others descended from those survivors after generations of selection. Still others arrived later from neighboring temperate seas. Together they assembled a biological landscape that now feels ancient only because human experience is too brief to witness its construction. The emperor penguin belongs to this newer Antarctic story. Its lineage reaches back into a much older radiation of penguins, including forms that lived when the Southern Ocean was warmer. But the giant penguins themselves were not simply reduced into modern emperors. Several evolutionary branches survived the Great Transition at smaller sizes, while the enormous forms disappeared. The emperor became the largest living penguin, reaching roughly 120 centimeters, about 4 feet, in height. Yet even this remarkable bird occupies only a modest remnant of the body sizes once produced by penguin evolution. The leopard seal carries a different history. It is a powerful modern predator, but it did not inherit the ecological throne of the ancient Antarctic whales and sharks. Its ancestors entered the Southern Ocean from temperate regions, and its present role developed within the colder ecosystem that emerged after the earlier predator guilds had vanished. Its existence, therefore, reflects recolonization and adaptation rather than uninterrupted dominance. Below the surface, the same pattern appears in stranger forms. Nototheniod fish transformed their physiology to function near the freezing point of seawater, producing antifreeze glycoproteins throughout their bodies. Ice fish went further, abandoning functional hemoglobin and relying on the unusual oxygen capacity of cold seawater. Brittle stars, brachiopods, sponges, and other seafloor animals likewise became abundant within a benthic community shaped by the absence of the shell-crushing predators that once occupied those waters. This distinction matters because the word natural can suggest permanence where none exists. A living ecosystem is not a fixed design waiting to be preserved. It is a temporary arrangement produced by climate, geography, competition, extinction, immigration, and evolutionary history. The animals surrounding Antarctica today are therefore not incorrect inhabitants. They are the inhabitants suited to the conditions that exist now. Seymour Island makes that lesson tangible. Its fossil layers preserve an Antarctic sea in which sharks hunted through warmer water, ancient whales occupied immense feeding roles, and giant penguins moved through an ecosystem unlike the one beneath today's ice. Around 52 million years ago, the animals best suited to those waters were profoundly different from those we associate with Antarctica today. There was no single Antarctic nature waiting to be restored. There were successive versions, each complete in its own time, each shaped by the physical world surrounding it. The frozen Southern Ocean is one frame in a much longer planetary film, and the creatures living there now are not the beginning of the story. They are one of its later chapters. Under the ice, Antarctica keeps most of its geological memory out of reach. The continent's great ice sheet averages about 2,190 meters, roughly 7,200 feet in thickness, covering landscapes and sedimentary basins that could contain an immense record of ancient life. Beneath that frozen surface lie rocks deposited when the climate, coastline, and surrounding ocean were profoundly different. Yet for now, much of that history remains inaccessible, sealed beneath a continent of ice. Seymour Island offers an unusual opening into that buried record. Because much of its surface remains exposed, layers of sedimentary rock can be examined directly rather than recovered through kilometers of ice. Its rocks preserve marine deposits from the Eocene, allowing paleontologists to trace changes through successive layers and compare communities that lived before and during the transformation of Antarctica. Without this exposed archive, the ancient Antarctic Ocean would be far more difficult to reconstruct. The evidence itself is rarely dramatic when held in the hand. A fossil may be a single shark tooth, polished by time and separated from the jaw that once carried it. Elsewhere, a fragment of a penguin leg preserves the shape of bone built for a vanished way of life. A section of whale jaw records an animal whose body is otherwise absent, while a broken shell can retain marks left by a predator feeding millions of years ago. Each fragment carries only part of the story, yet each part constrains what the larger story could have been. The value of these remains comes from their relationships. A shark tooth found within one sedimentary layer can establish the presence of a predator at a particular stage of Antarctic history. A concentration of shells can reveal the abundance of animals living along the seafloor. Changes in the kinds of fossils appearing upward through the rock can trace ecological turnover, while microscopic remains can record shifts in temperature and ocean conditions that larger fossils cannot preserve as clearly. Layer by layer, the rock becomes more than a collection of specimens. It becomes a sequence of vanished communities. The fragments also preserve something that photographs of Antarctica can never show: ecological succession. A tooth embedded deeper in the formation belongs to a different community from one found higher above it. The arrangement allows scientists to watch abundance, disappearance, and replacement unfold through geological time, not as a single catastrophe, but as a changing pattern written across successive surfaces of ancient seafloor. In this way, even incomplete fossils can reveal movement in the larger ecosystem. The absence of fossils elsewhere is also meaningful. When most of a continent is hidden beneath ice, the absence of exposed rocks does not mean the absence of ancient life. It means the evidence remains physically concealed. Future scientific drilling, seismic studies, and advances in subglacial exploration may reveal older landscapes beneath Antarctica, including records from periods when forests covered parts of the continent and temperatures were far warmer than today. Those deeper layers would extend the story beyond the vanished Eocene ocean toward worlds separated from the present by immense changes in climate and geography. Seymour Island, however, preserves something more specific. Its fossils capture the moment when a warm marine ecosystem gave way to the cold Antarctic world that followed. Beneath the feet of researchers, fragments of teeth, bones, shells, and sediments remain as the surviving pieces of a sea that no longer exists. The ocean around Antarctica does not carry the memory of the animals that once lived within it. Water moves through the same broad basin, driven by winds, density, and the shape of the seafloor. Yet, the creatures that once occupied those currents have vanished so completely that their existence depends on fragments preserved in stone. For a time, this was a remarkably complete marine ecosystem. Sharks occupied several levels of the food web. Enormous whales moved through the upper waters. Giant penguins entered the sea from the shore, and predators hunted across the seafloor. Their disappearance was not the result of a single failing species or one biological weakness. The physical setting that supported them changed beyond the range in which that community could continue. Continents do not move with any sense of purpose. They drift because the plates beneath them shift over immense spans of geological time, gradually altering coastlines, gateways, and the routes available to the ocean. As the passage between Antarctica and South America widened, the circulation around the continent changed. The formation of the Antarctic Circumpolar Current helped isolate Antarctica from warmer waters, while falling atmospheric carbon dioxide contributed to a broader cooling climate. Together, these changes transformed the environment without requiring the animals themselves to become less capable. That distinction reaches far beyond Antarctica. Evolution can refine a creature for the world that exists, but it cannot negotiate with a continent in motion. A predator may possess excellent senses, powerful muscles, or an efficient metabolism, yet none of those traits can compensate indefinitely for a fundamental shift in temperature or ocean circulation. When the physical conditions disappear, the advantages shaped by those conditions can disappear with them. The ancient community also demonstrates how little protection abundance can provide. A system may contain many species and intricate relationships, yet its complexity does not make it independent of climate. Each feeding relationship ultimately rests on suitable water, suitable chemistry, and a circulation pattern capable of sustaining the productivity beneath it. When those foundations shift together, an entire network can contract even while individual species remain biologically capable. The modern ocean is held within another arrangement of boundaries and currents. Its temperatures, chemistry, productivity, and circulation depend partly on where the continents sit and how their coastlines guide moving water. The Antarctic Circumpolar Current now forms a vast ring around the continent, linking the Atlantic, Pacific, and Indian Ocean basins while restricting the exchange of warmer surface waters with Antarctica. It has persisted for roughly 34 million years, making it one of the enduring features of the modern Southern Ocean. Yet even this immense current belongs to a particular moment in Earth history. Its existence is not a permanent rule written into the planet. Another configuration of continents, another change in ocean gateways, or another alteration of climate could eventually reshape circulation again. The timescale would be almost impossible to witness within a human lifetime, but geological change does not require an audience. Beneath the ice, deeper layers of rock may still contain chapters that have never been opened. Some could preserve marine communities older than the Eocene, perhaps from Antarctica's warmer past, when different coastlines and different currents connected habitats that no longer exist. Each buried layer would extend the record farther from the world familiar to us. The same water that once carried ancient whales and giant penguins now moves through a colder ocean governed by different boundaries. Its molecules have no history, no recollection, and no awareness of what passed through them. Only the rocks remember. In them, an ecosystem that seemed established for ages remains preserved as evidence of something geology makes difficult to accept. Permanence belongs to no living world.